It's good to be back. Hadn't been here for a couple months here. Hope everyone's having a happy new year. We've got on a few more days we can say that. Since the end of January, we're already into that year. So I'm going to start off with the big story that I think most of you probably have heard about, and that is this search for Planet Nine. Constantine Badagian, I don't know quite how to pronounce his last name, and Mike Brown put out a release this last month that is almost like a discovery paper in the sense that they really think this planet is out there. And Mike Brown is famous for this book, and if you haven't read it, it's actually a very good read. And he is the one who discovered this dwarf planet Eris, which turned out to be the thing that brought Pluto down because it was more massive. It's actually about, I think, 20% more massive than Pluto. They thought it was bigger, but it actually, the Pluto flyby confirmed that Pluto is actually still the biggest of the dwarf planets in the Kuiper belt. So it's kind of interesting that he's now getting around to replacing Pluto with his own ninth planet here. I don't know how the discovery is going to go because, as I tell you, they haven't seen this thing yet. I don't know if his ears were burning, but I just got my Scientific American, and it has the search for Planet X, not 10, in there. But it's along the same vein, but in the February edition here, it's not Michael Brown's work that they're talking about there, but it's the same objects that they had there. So what is the scoop? Why do they think this planet is actually out there? Is by studying the orbits of these most distant Kuiper belt objects, ones that are actually out beyond Neptune, which is similar to Pluto's orbit. But the interesting thing is these are all orbits that you see here in the purple here that are they don't get that close to the sun. They're outside kind of the control of Neptune's orbit. And when they were looking at these 6 here, which represent the sample of these types, Sedna being a very famous one here, which takes, like 10,000 years to get around, they found that they all seem to swing out of around the sun in the same direction of the sky. So if you had an orbit like this one here and just the sun, it would always stay in that particular orbit. But under the influence of other gravitational bodies, all of these elliptical orbits actually precess around the sun. So they're like, as Mike Brown said, they're like hands of a clock that would, without any other influence, would just randomly go around here, and it'd be like looking up and seeing 6 hands of a clock all moving at different rates, and just happen to look up and see they're all pointed in the same direction. So that was a big clue that something else was controlling these orbits. And the thing that they did that I think is what the convincing part of all of this is, they played with some other objects in there to try to figure out how to control these and keep them in these orbits. And what they found, that the answer was putting in Planet 9 right here, where its closest point was 180 degrees kind of out of phase of the closest points of all these other orbits. Everyone see that there? So it's in the opposite direction there. So and that pulled everything together and explained all of these orbits. It also explains why orbits like Sedna, which doesn't get close to Neptune, gets way out here because of the influence, of that planet over here. And the thing about this orbit here is that it not only controls that, but it's going to control some other objects in the solar system as well that they did not at least set out to find. So you would think that this would knock these out of the orbit. But if you have orbital resonance, in other words, if these things go around, say, every 10 times, this goes around 4 times, or vice versa, then they won't throw things out of there. And Pluto and Neptune actually exchange a similar resonance orbit, so because Pluto crosses Neptune's orbit, and it doesn't get thrown out because of that same reason. Okay, I thought this would explain everything. I looked at his paper, and so if anyone has any questions at the end, I'd be happy to answer that. Here is a nice little movie that they created so you can kind of see the three dimensionality of those orbits. So you can see that, first of all, they have that elongation. They're pretty much in the same plane, and they'll go around them here so you can see they're off in that same direction. And then they'll overlay the planet 9 here. And then as you see, you swing around here, that's in the same plane but counter to those other orbits there. So that's where they think that is at. Okay, and you know, one of the things when they were doing the modeling of this is, here's those orbits again with planet 9 right here, is that the models were predicting other objects that would be going out perpendicular to the plane. And so the modeler, Constantine, would come back and say, well, my models are saying that these other objects are out here. And Mike Brown, who's an observationist, said, wait a minute, we have objects just like that. So they kind of killed a couple birds with one stone here on that. Well, what is this thing? Well, their models suggest that it's an object that is about 10 times the mass of the Earth. And knowing what we know about the mass and how it relates to the size, this is kind of the object size that would be compared to Neptune. So just a few Earth radii, maybe 2 to 3 Earth radii. Being 10 times the mass of Earth, it would be gaseous there. And we'll talk maybe a little bit more about, you know, why is this thing out there. But there's the size of it. And where do they think it's actually in the sky? And this will take a little bit of explaining, but let's look at this top plot right here. This is declination versus what we call right ascension. This is the coordinates that astronomers look out onto the sky. It's basically the Earth's latitude and longitude extended out into space. And this big black path that you see here is where they think this particular object is. This blue path is actually the what we call the plane of the ecliptics, where all the planets lie and where the sun would lie. So we see the sun in the northern hemisphere way down here at minus 23.5 degrees declination in the winter and 23.5 degrees north of the equator in the summer. So those are our quasar seasons. Notice that it's not on the same as ecliptic, and that's because the plane of which this planet and those other objects I was showing are actually tilted relative to the plane of the ecliptic there, about 30 degrees, I believe it is. And then these red lines over here is actually where you would find the Milky Way on the sky. And that's significant because in those areas you got a lot of stars, and so it's going to be hard to find this object in these areas right here. Here's their best guess here on this next plot, again against right ascension here, is how far it is away from the sun at any given time. So there's this band right here. So at the closest point, it might be getting about 200 astronomical units, an astronomical unit being the distance between the Earth and the sun. But there's a span of that, you know, maybe anywhere between 200 and looks to me like 400 there. And then out here, when it's furthest away, we don't, it doesn't have much influence on the rest of the orbit, so they don't really have a good number of that. So it can be anywhere up to like 1,000 astronomical units in this spot over here. Here's an indication of the magnitude of it, of the star. Being astronomers, we do things backwards. The higher the magnitude, the fainter the object is. Okay, so when it is closer, it has a lower V magnitude, meaning it's brighter. Okay, so this is significant because we have to see what our telescopes can actually see in that parameter space. And then this here is just showing how fast the object is moving in its orbit in units of arc seconds per hour. Arc seconds being an angle on the sky. An arc second is about the angle a dime would subtend at a mile's distance. Okay, so it's a very small angle. So every hour, if you were to look at that object in the sky, you would see that it would actually move relative to the stars, whatever you read off of here. And so the interesting thing here, so it's moving its fastest when it's closest. And that's what happens in the elliptical orbits. And it's slowest when it's further away here. The most distant object that we have found right now is Eris, and it moves at 1.5 arc seconds per hour. So a lot about the searches for this object are going to be tough because they move slower, and they haven't been geared to look for that slow of objects out there. So it probably has been seen in some of the larger telescopes, or is possibly, but they would have never noticed it because it wouldn't have moved. And of course, you have to make multiple observations to find this object. So this plot is actually showing against the magnitude here and kind of the parameter space of various searches that they have out there that looks like we can cover it pretty well when it's close here. The problem here in the center, and they have WISE question that mark, that's the Wide Field Infrared Space Explorer, I believe, spacecraft that did a survey that might have been able to detect it in here, but there's a lot of Milky Way objects in there. And so that's where things get confusing, and it's always going to be very difficult to find it in this region here. It spends less time in this region because it's moving faster through that area. So chances are it's in this area over here where we haven't got sufficient capabilities to see it in that region of the sky. But the big one that everyone's kind of pointing to is whether we get the Large Survey Synoptic Telescope, LSST, which will take, essentially very deep images on the sky over wide swaths of the sky, that will have a good chance of seeing it over here. Fortunately, Milky Way's over in this direction as well, so there's going to be some difficulties. But anyway, they were very confident about their results, and they put this out because they want people to start looking for it. And so this is going to be a good thing. If they find it where they say it's going to be, that's going to be a great thing. So, and the power of science and math to figure these things out. Okay, so the other kind of significant thing about this find is its size and everything. We know from the Kepler study the distribution of planets that we see out there and what sizes they have. And this is a plot of, I don't know how many, 3,000 candidates that they had associated with the Kepler mission. Here are the sizes of relative planets, here being Jupiter, Neptune, what we call super Earths here, and everything smaller than Earth here. And this object is somewhere between it's probably in this bin here, 2 to 6 Earth radius, maybe right on this line right in between here, 6 being the size of Neptune. Well, these are the most common sized planets in, our Milky Way galaxy. Yet we didn't think we had one in our own solar system. So it's looking like we actually might have one, which would be great because it'll be close enough for us to ultimately study and find out what this most common object even kind of looks like. Is it truly gaseous? What are the differences between it and some of the larger gas giants? So it's very exciting. So, obviously stay tuned. So hopefully we will find this thing quickly here. And it's like nothing else that we have in our orbit, in our solar system. The theory as to how it got there is it was a fifth gas giant or in the solar system when the rest of them were formed. We know that Jupiter and Saturn, Uranus and Neptune all moved around, and that this one potentially got ejected into this outer orbit at that earlier time in the formation of the solar system. So Kim Evans, who's filming back over there, helped put this together here, which I thought it would be good to do a little solar system model here in honor of the Broncos playing and everything like that, and football season here. So we set up a little scale universe here, or scale solar system, I should say, and got our 100-yard field over here. The beach ball, which is about 1 yard across here, is at the goal line over here. And on that scale, Earth would be a little bit smaller than a dime out here at the opposite goal line. Just take that in for a little while. It's easy to see all this stuff around here, but remove all of that stuff, and you really think how empty space really is, okay? And that's one astronomical unit there. We're going to zoom out to what kind of was our edge of our planets, solar system, Neptune here, in this next movie here. Okay, we are out to Neptune's orbit right here. You can still kind of see the stadium over there, right? And this is about 1.5 miles out here, so about 3 miles in diameter here. So you can see some of the cities. Here's downtown Denver here. So about that size for the solar system, getting pretty small. Okay, well, let's do our last zoom here, and that is out to our planet 9 on that same scale. And there you go. So we're going out to Broomfield and down here south of Castle Rock. And that's the low end of their estimates. So both of these can be extended almost twice as far out in this planet. So we have nothing else like that. Okay.